Well, good afternoon and welcome, Vaat. Thanks for having me. As I said, ammonia is a renewable fuel. Presentation is built up as the following. We see that the necessity in renewable fuels in general and why ammonia of all the renewable fuel options will be addressed first. And we'd like to dive into the technical feasibility and then later on also some economical aspects at the end. And of course, when we talk ammonia, we also need to talk about safety, with also some outlooks on future developments. So, renewable fuels. Well, the main motivation for renewable fuels might be known to most of you. Just as a reminder, energy saving and the application of fossil LNG alone is not sufficient to reach these goals. So, renewable fuels are definitely hard to have a part to play. Then when you look into ammonia, ammonia is actually not really well known as a fuel. Just keep it here. Normally I'm used to walking, but sure. Ammonia is mainly used as a compound, as a vital compound for fertilizer. And the global production passing 180 million tons. So it's very well scalable, it's all synthetically made. Of course, this is still the gray method, as we consider, because it's the hydrogen which is used to make ammonia is obtained from natural gas rather than the preferred way in the future where it's green ammonia, where hydrogen is obtained from electrolysis of water, preferably again with renewable energy. Nevertheless, the ammonia is ammonia, either way it's produced. So the knowledge and experience in these industries is very valuable to translate it to a fuel. Furthermore, it's used in cooling systems and also in DNOx systems, which is then again in the form of urea, which is a CO2 ammonia combination, but also a very known technology. Then some history. The oldest one I could find is 1935, which is the director of Casale, which is an ammonia plant producer. So these guys have ammonia plants, and instead of going to a petrol station, he thought, I have my own ammonia plant, I'll let my car run on ammonia. It did so by cracking part of the ammonia back into hydrogen, making ammonia hydrogen blends, which is then comparable to methane combustion properties, and then indeed combusted with the spark ignition. Also, with the lack of diesel during the Second World War in Belgium, we see ammonia coming in, and also in the more modern applications, most of them dual fuel, are very technically feasible. So then, why ammonia of all renewable fuel options considered? First of all, I would like to have a few words on bio versus synthetic. Of course, bio has a lot of potential in the near term, and as the availability is already there to some extent, but the scalability is somewhat limited, and also not all bio is fully carbon neutral. So I definitely think bio has a part to play, and it has a very good role, but then again, looking at the maritime industry, we'll need to diversify and share the market with different fuels. Then when you go to synthetic, which is better scalable, you run mostly into these type of options. The most well-known one, of course, is liquid and compressed hydrogen. This, and for the record, this is without the consequences of a tank. So the mass of the tank and the shape of the tank do not include yet in these parameters. Nevertheless, the main parameters are very clear with the conditions you need to store it in, but also the cost, which is sometimes overlooked to produce it. Because when we look at it, hydrogen has a clear disadvantage in volume, but in the production cost, it's one of the most attractive, consider it's the main simple and short compound you can make. If you go then to improve the volumetric energy density with carbon carriers, for example, which are also great. Methanol is also one of our research we have ongoing at the moment. We see that the production costs are relatively quite high compared to the pure hydrogen. And then the nice thing about ammonia is that, yes, it is less volumetric energy dense than the carbon carriers. However, it's a significant improvement already compared to pure hydrogen, and the production costs are in the same range. Of course, this is based on certain assumptions, certain sizes, so please check that out before just blindly following that figure. But it's a guideline to compare fuels with them, with each other. It's a very clear distinguishment. So it's really a balance between volume and cost in the end, which will break through. And in my view, in that sense, ships, there is not a single fuel which will cover the entire market. Each ship type has its own preferences based on mass, volume, but also fuel costs. And ammonia, I think definitely ammonia with the fuel cost in mind is very attractive for long distance, big vessels, and where the smaller vessels, where ammonia becomes too impractical because it does require some measures. Methanol might be a bit better, and of course, if you can fix it with pure hydrogen and possible addition to a small amount of batteries for very short distances, sure, you could work with that. And I think it will be a blend, but these are the main reasons for us to also investigate ammonia and push the renewable fuel market ahead. So that's the reasoning behind ammonia. Now we go into technical feasibility. And to look at it, we first need to realize what ammonia is. And ammonia is a flammable gas. Yes, it's relatively harder to ignite because the lower limit is quite high. This is one of the highest lower limits I've ever found compared to other fuels. And also the bandwidth is not that wide. Furthermore, the auto-ignition temperature is very high, it has a low flame speed, and it consumes a lot of heat when it evaporizes from a liquid to a gas, which is all not the most favorable property you could have as a fuel. Nevertheless, it can definitely be done. Furthermore, of course, it's highly toxic. Small note on that, you can also very well easily detect it. So, because everyone can smell ammonia when it's above 25 ppm. Of course, when it's very too high, beyond 3000 or even higher, then you might not even notice it by smell, but you might notice it by other symptoms. Anyway, yeah, I wouldn't recommend that. So, but you notice it at a very early stage, and that's vital. Then, considering these flame properties and the possibility of cracking hydrogen out of ammonia, also ammonia hydrogen mixtures are considered within this study, because ammonia hydrogen mixtures definitely improve all these flame properties and are capable of replicating those of methane, which is again lessons learned from LNG, very vital to make the next step. Then we basically drew down everything we knew, or I drew down everything I knew, how you could convert it. So we start with the steam turbine, which is very old-fashioned, of course, but yes, with ammonia you can burn ammonia. With the heat you can make steam, and steam can propel a steam turbine. So yes, this could be done. Then we have a gas turbine, more efficient and more compact, definitely. Then of course the very well-known internal combustion engine, both compression ignition and spark ignition. Then we have fuel cell technology, of course, more and more. Then we have the PEM, which is already quite mature and already applied in cars, buses, heavy trucks, but also submarines. So this is becoming more and more into play, but then hydrogen storage is the bottleneck in that sense. So if you can work with pure hydrogen, PEM is a great solution. If you don't have pure hydrogen, it might be very tricky because you need to crack and purify your ammonia. PEMs do not tolerate ammonia that much. It's down to, it's below 1 ppm. I think it's even 1 ppb. So that's parts per billion. So it needs to be very pure because ammonia will pollute your PEM. Alkaline does not require purification, but does require cracking. And then preferably, of course, the salt oxide fuel cell, which can handle ammonia directly. Well, long story short, they're all feasible, technically. If you're happy with the performance, that's an entirely different matter. So, looking into what we're talking about here is that ships, and in this case specifically the ammonia carrier, because in our view, one of the first vessels which will use ammonia are the ones already carrying. Of course, you will not find ammonia carriers on marine traffic because they're all camouflaged as LPG tankers. Because ammonia and LPG again have a very nice bond because the storage conditions are very similar. So again, lessons learned from those, and also engine developments on LPG, on the LPG front, can partially be applied for ammonia as well. Then when you look at storage, we had a great picture about the saturation pressure. And as you can see here, the smaller ones are fully pressurized, 10 bar. Then we have fully refrigerated, it's minus 34. And then we have everything in between, which is 2-3 bar with minus 10 or something. So this really demonstrates that when you go up into scale, you don't want to pressurize it, you want to cool it, because this is far cheaper in tanks as well. But it mainly demonstrates that efficiency is a very dominant parameter. And when it comes down to converting ammonia into power, we see the ammonia hydrogen blends. In case you only consider renewable fuels, ammonia diesel, I will come later to. Ammonia hydrogen blends are the most interesting. Steam turbines obviously are not sufficiently efficient. Gas turbines also do not win the battle on efficiency compared to the internal combustion engine. Of course, a combined cycle could be considered, but that would have been too much detail, and also combined cycles are not that often used in general, also with fossil fuels. So we mainly stick to the internal combustion engine, and also with few fuel cells for the future development. We definitely also included these types to assess the new technology and where they are now and where they need to be implemented. Then system introduction. So to compare apples with apples, it's a two-stroke. We have the tanker, which is for the internal combustion engine, a two-stroke inline. So we have a direct connection to the propeller shaft and the hotel load. And this is the products which are effectively supplied to the vessel. And then you need an entire system running. So we have the big vessel here, which is stored ammonia at minus 34. Then we have boil off, because it's atmospheric pressure and cooled, so part of the boil off can be used. And also, boil off is not that high, so when the engine is running, it will, on high power, it will definitely also need to evaporate part of the gas, which is fine. It's relatively simple. And then, of course, you need to crack part of the ammonia gas. Of course, this gas will also be polluted with nitrogen and parts of the ammonia, but that's not too bad, because you inject ammonia anyway. So if you incorporate that in your blend, you can definitely manage it. Furthermore, of course, you could also debate that it should be a liquid injection. I think for the two-stroke MAN, it will be indeed a liquid injection, but for now, it was assumed as gaseous injection. Furthermore, you see a conventional power takeoff with some electrical losses there. That's the system introduction for the internal combustion engine. Before going into fuel cells, I would like to address the most, or at least from the public's point of view, the most concerned topic for ammonia, which is NOx, and possibly also N2O. Going into this, it was very nice to see that when you study IMO T2 levels, the scale of the engine doesn't really matter. It's mainly the operation, so the rotational speed of the engine. And when you go to experiments done in the past and present for ammonia, so real tests, but also, of course, experimental studies, they show that actually the small engines on high speed do very similar when it comes to ammonia hydrogen combustion. So to say something about this, we need to understand why these are in similar ranges. When you look at the physics, we of course expect more NOx in a sense because we have more nitrogen. Nevertheless, the average temperature of the entire exhaust gas with ammonia and hydrogen is lower compared to diesel. Furthermore, with ammonia hydrogen compression, it's a homogeneous blend. So where a diesel is of course they spray it out over a wide area, ammonia hydrogen is more homogeneous, so also peak temperatures are lower. Then we have a very interesting topic, which is the diesel dilemma, which is what they used to call dilemma between high temperatures, high efficiency, low PM, but high NOx, or reduce PM or reduce NOx but have higher PM by cooling. You do not have particulate matter in any sense, also no sulfur. So in that sense, you are free to cool it. However, cooling it could definitely have an adverse effect on efficiency. So this is a balance to be found later on. In my view, you should focus on efficiency and apply after treatment anyway to go beyond IMO T3 and really reduce NOx as much as possible. Then a very interesting part is also the selective non-catalytic reduction, because ammonia slip could also very well reduce the NOx formation within the cylinder. This is of course to be very further researched and confirmed, but the principle of ammonia, and also here you see it within the DNOx system applied with urea, so you see the ammonia CO2 bonds, but it's actually the ammonia, or actually the hydrogen in that sense, doing the work, because the nitrogen combines with the nitrogen and the hydrogen combines with the oxygen, making them again harmless. So there's still emissions, but no harmful emissions. And that's how it works. So definitely part of the unburned ammonia could also be responsible for that. Of course, this depends also on the engine and the operation. So from a literature study, based on that, we conclude that for now, it should also still be in similar ranges. It could very well comply with IMO T2, or just about. But either way, to comply with IMO T3, we definitely have to have SCR, which is fine in my view, because also ammonia DNOx systems, they're already commercially available, they run very well, and they run on ammonia in the end. So we didn't see a big issue there. It also, in that sense, covers the ammonia slip if you might have it. Onto fuel cells. For fuel cells, again, we have the same output, so propeller shaft and hotel load. But again, this is the point, because you're converting a ship which is sailing fuel direct, or diesel direct, more commonly known, to a fuel electric configuration. So the losses of the electrical system are an addition in this sense to the fuel cell configurations. However, when the ship are already fuel electric, fuel cells might become more interesting earlier. Nevertheless, you see the electric system, but also the cracker, which requires heat input because the PEM is a relatively low temperature, so this is a loss. Also the purifier needs to run, so also that is a small loss. And of course they require space, but in energy sense it's less efficient due to these parts. But still, if the PEM is still efficient enough, it can do very nicely. Moving on. And the alkaline fuel cell, similar setup, only no purification. And then the most preferred fuel cell in my view, which is the salt oxide fuel cell, it can completely drop everything here and focus on direct usage. Then, when you start comparing them, and of course this is with a note, because the salt oxide fuel cell is going through a lot of developments, of course all fuel cells are, but especially with these notes, of course this is a moment in time, and also with certain assumptions, because I was already commented on that the load response for the salt oxide fuel cell for some technologies is already at similar levels as internal combustion engines. However, if that be so, they were not able to tell me what the consequence of that was to the power density. So it really shows that the salt oxide fuel cell has a lot of potential, but still has to become more mature to be actually implemented. It also shows that the others are quite well performing overall, and we'll get to efficiency in a minute. And still, of course, some emissions remain with the internal combustion engine. When you look at the system efficiency, we see that solid oxide fuel cell in the end wins it, or is the best compared to the others. Nevertheless, it is also very costly at the moment. So even though it's more efficient and it compensates its higher capex with lower opex in fuel, it still doesn't beat the internal combustion engine today. So again, a longer story short, we see that the internal combustion engine is the way to go for now, and the fuel cell has a lot of potential for the future, but needs to become more mature. So if you would like to use ammonia within the near term, you definitely have to stick with the internal combustion engine. Then it is of course an interesting discussion to compare compression ignition, which would be homogeneous charge compression ignition, which has its own challenges, which I could also elaborate on, but for the sake of time I will not. But of course spark ignition will offer you the most flexibility in operation of the engine. But either way, this is something to be further investigated. But for now, the internal combustion engine definitely seems the way to go. When you compare it to have a fuel oil, the conventional configuration, again, same setup here below, but now you have heavy fuel oil. It shows significant differences actually mainly in harmful emissions, obviously, but also in cost. And this is based on 25 years, but also a very conservative fuel oil price, because this is based on a Dutch sustainable energy prices. And of course, the Netherlands is not renowned for its sun. Of course, it does some wind, but it's also not the cheapest. So it was a conservative ammonia price of 850 euros per ton. In respect, ammonia costs about now, grey ammonia costs 300 euros per ton. And there are numerous places already which can deliver green ammonia at around 400 as well. So then it becomes really competitive. Because when we look to cost in a further extent, this is making it more interesting. Because some places are already capable of delivering green ammonia around at these ranges. Of course, they need to expand and grow, but the pilot plants are definitely there. And you see that when you look at energy, because that's in the end, in my view, to compare apples with apples, the blue lines, and obviously you see back the lower heating value, because 600 euros per ton HFO is in the range of 300 euros per ton ammonia, obviously. When you introduce added value of clean transport, for example, by means of CO2 taxation, you can level the playing field quite nicely. So these are aspects to consider, because in the end, yes, for now it's not economically feasible. But if a ship owner finds a cargo owner who's willing to pay more for clean transport, it could make a world of difference, because transport costs for most products are just a very small amount. However, for the ship owner, it's a huge difference. So that's the first part you could help and accelerate the adoption. Furthermore, of course, making fossil fuels more expensive could be very helpful. And next to that, of course, the main bottleneck at the moment is the amount of renewable energy. If we expand the renewable energy production, costs will go down, and also the renewable fuels made from the green electricity will go down as well. A small view on time. For me, indeed, ammonia hydrogen was investigated, so that was the research based on. However, to make such a jump is quite radical for a ship owner. Ship owners are relatively conservative, and I understand that, because they make huge investments, they need to work with them for 20, 25 years, maybe some 30 years. So to be able to fall back on reliable technology, which they know, is very important. And ammonia diesel does enable this, because in case the ammonia system would fail or not work in any way, you can always go back to full diesel combustion, which guarantees the operation of your vessel, which is vital. And with ammonia diesel, you can go to very high ammonia blends. So think about 95% ammonia, 5% diesel in terms of mass, which is definitely feasible. Then you have already significant reductions. Of course, as long as you have internal combustion engine, you will definitely have require SCR, but this can definitely be arranged. So ammonia diesel is a vital intermediate step. It could also be considered that you skip this step by extending the ammonia diesel period and awaiting salt oxide fuel cell developments. Either way, lots of ongoing, but definitely ammonia diesel seems to be the first station for ammonia. Then some words on safety. I will start with this because safety is quite a perceptive definition, because they all seem safe. I mean, this is industry we've done for years, and also new industries offshore done for years, more and more. But either way, they can go wrong. And you might not know, but these things happen, and these things occur, but they don't withhold us from continuing doing this kind of business. So we need to draw a line somewhere, what we consider acceptable and what is not acceptable. And yes, there will be incidents, but we have to reduce the likelihood and the severity of these incidents. And still, then you need to find a balance. So when you look at ammonia, you normally fall back to rules and regulations, which is the first guideline for safety as well. You see that a lot of regulations are already in place when it comes to bulk transport, similar to natural gas. However, when it comes to natural gas, with the IGF code and the IGF code eventually adopted, it's already implemented as a fuel as well. However, for ammonia, of course, the IGF code is a very nice and important foundation for ammonia as a fuel, but there are no specifics. So risk-based design is essential. And when you do risk-based design, you just need to use common sense, look at the physics, and try to assess it. When you do so for ammonia, and here you see ammonia, compressed natural gas, liquid natural gas, diesel, and ultra-low sulfur fuel oil. The reason is ultra-low sulfur, because HFO is such a variety that the safety data sheet did not specify what HFO really is, because it varies from point to point, where ultra-low sulfur fuel oil has very strict requirements. So when you compare them on flammability, we don't see much new items occur, because flammability of a gas is relatively well known. Also, when we look to the environment, although the impact type is different, it's definitely labeled already as very toxic to aquatic life with long-lasting effects, which is known in the diesel variants. However, ammonia is toxic if inhaled, and also causes severe skin and eye damage on high concentrations, obviously, which is totally new compared to the other fuels. So this is an essential addition to safety when you do such an assessment. To summarize that, the flammability limits, of course, show the flammability risk. But when you compare flammability with toxicity, you see here about 3,000 ppm on a short duration of time is lethal. Level 3 is lethal. Whereas 15%, which is 150,000 ppm, is far out of range. So compared to the 3,000. So all toxicity alarms would have gone off before it become even flammable. Of course, spaces where high likelihood of concentration of ammonia are present, it's definitely needed to also incorporate flammability measures. Furthermore, of course, the toxicity to the environment remains and is also a very specific continuation of that. To do so, I set up a fuel system diagram, and I'll walk through it by identification, analysis, assessment, and mitigation, all based on similar guidelines of the IGF code. When you look at it, also the risk matrix used as a qualitative assessment is based on the IGF code with a more conservative color coding, because it was done by one engineer with a limited amount of time, summarizing everything. So people, and assets and environment, all covered. To do so, also a workflow was determined. So we defined the failure mode with the various calls, or you define a cause, then an effect, and also some detection. Why it says none, I will explain in a minute. Based on that, you can make an original risk ranking, and based on the ranking, you determine if mitigation is required or not. And then you can assess it again with your mitigation supplied. Doing so, I find it quite important to be as non-biased as possible. So the fuel system diagram I started with had 0 safety measures. Even the obvious ones, I did not include them. Why? Because I wanted a valid reason to include it or not. So to be as non-biased as possible yet again. Based on that, we'll do the assessment, we reflect on it, and also do a second assessment and reflect on the additional mitigations I applied, if these mitigations also did not add any unacceptable risks. Doing so, I of course had to make some boundary where I stop. So in normal operations, I assumed no leakages. Of course, this could occur, especially when you look to natural gas. It sometimes occurs, but also in cooling systems, ammonia sometimes. It's very good, nearly there. Of course, also the engine itself as a block was assumed inherently safe. So no leakages once it's in the engine. which is also very dependent on the time you inject the fuel. And ammonia and hydrogen are labeled as fuel in the ammonia carrier and no longer as cargo, which is also vital in rules and regulations. I'll add some color to this. You would see that the beamer does translate it a little bit. Okay, believe me, this part is green, and this part is orange. What we see here is the liquid part coming from the cargo hold directly, which needs to be evaporated, and then of course the boil off, which is normally compressed back again into the tank, now can be used with a compressor and combined with evaporated ammonia here. Then it's separated with part ammonia injection with the gas regulating unit and gas regulating unit for hydrogen, which is cracked here. That's what it basically comes down to, and it's all in the engine room, and it's all single walled. Then, when you assess it, you definitely encounter lots of risks, which are unacceptable, because red is unacceptable, yellow is tolerable but should be reduced if cost effective, and green is acceptable. Well, obviously, ammonia leakages are very dangerous, so they rank in the red area, and also other items like unable to supply fuel resulting in a gas ship are also unacceptable. So again, assessing that really shows the necessity for mitigation. When doing so, actually the type of mitigations are very similar to the ones in natural gas. However, ammonia should never be labeled as natural gas, but the lessons we learned and the technology we have from natural gas are very useful, because it all comes down to detection, ventilation, pressure relief, and isolation. Furthermore, of course, routing of piping from a certain distance, double wall piping in certain spaces, and of course redundancy. So don't be shocked, but it does blow up the system a little. Again, I'll add some color. Here you see the liquid supply with evaporation, and of course the boil-off supply. And don't be fooled, this is just mirrored to cover the redundancy. And you also see that all the equipment is in a separate room. So all the piping is also in a specific trunk or in a specific room with ventilation and detection. And once it goes into the engine room, you see that double wall piping is applied, and pressure detection on the double wall piping is to gas the double wall piping. Again, also redundant. Ammonia diesel, however, would offer a lot of benefits, because all the redundancy could be covered by diesel, so all the redundancy of ammonia can be skipped, and also the cracking would no longer be required. So again, a really 80-20 rule of 20% of the effort can already result in 80% of the result, meaning that ammonia diesel is definitely attractive because it reduces the investment cost in that sense. In that sense, also the redundancy was first applied 2 times 100%, but this is definitely not needed, because the main requirement was adequate ship speed and maneuverability, whereas 2 times 50% will definitely suffice that requirement. So it was reduced in scale, just to cover lower capers. Also, that assessment, investigating these additional mitigations, really showed that, of course, there are more risks, but not on higher levels already encountered. As a conclusion, we've seen the reasons why ammonia could be attractive as one of the fuels for shipping, the technologies you can consider, and of course the safety measures you have to take. Some outlooks, of course, the timeline with ammonia diesel as a first step. So further research in combustion is definitely required, because we're the ship designer, we're the system integrator, specific components need to be further developed. And of course, this is just an ammonia carrier. Also, ships not carrying ammonia can definitely be one of the vessels to be investigated further. Also considering fuel electric configurations vessels already. Next to that, the hazard should be further detailed to further clarify and eventually define rules and regulations. As a small note, you might notice these are small battleships. I'd like to indicate. This is called crossing the T back in the day, which is the last time I recall using it was during the Second World War. But what I meant to say with this picture is that you see a lot of struggle between each option most of the time in the news, and people tend to forget what the goal is. the goal is to reduce harmful emissions and the use of fossil fuels with them. So I think none of them will cover the entire market. So we should focus on, together with each option applied, to really get the market to the goals we set out. Anything to add to that? Yeah, that's basically what it comes down to. All the research is publicly available in these links. Also, if you can't find it, feel free to contact me. And if you have any questions, please let me know.